Hi, my name is Nathan Stacey. I'm originally from Idaho, and I received my bachelor's in mechanical engineering from Utah State University. I'm currently a PhD student at Stanford University in the Department of Aeronautics and Astronautics.
So my research is focused on exploring small celestial bodies such as asteroids. There's a lot of interest in studying asteroids for three main reasons. First, studying asteroids has a lot of scientific value. Asteroids help us better understand the formation of our solar system and may provide clues to the origin of life. Second, asteroids contain valuable resources that could potentially be mined and utilized in space. Finally, we want to be prepared to protect ourselves if a large asteroid is ever on a collision course with the Earth. This image here depicts two upcoming NASA asteroid missions that will both launch within the next 2 years. A significant limitation, though, of asteroid missions to date is that they have required extensive human oversight throughout the mission. My research is focused on creating new tools to help future asteroid missions be more autonomous. I helped to develop a new multi-spacecraft mission architecture, shown in the middle, where each spacecraft captures asteroid images. Points on the asteroid surface, shown here as green dots, are tracked in the images, while measurements of the distance between spacecraft are also recorded. From this data, my new estimation algorithm is able to simultaneously estimate where the spacecraft are relative to the asteroid, the positions of the tracked points on the asteroid's surface, the asteroid rotational motion, and the asteroid gravity field. I developed a new technique shown on the right to make the estimation algorithm very computationally efficient, as well as new techniques shown on the left that make the estimation algorithm robust to uncertainty in the modeled spacecraft motion. Although I created these techniques for asteroid missions, they are beneficial for spacecraft navigation in general, including for Earth-orbiting satellites. I've also been working to validate my algorithms with hardware-in-the-loop using images captured from a real spacecraft camera in a lab environment. One platform we have to accomplish this is the Space Rendezvous Lab's robotic testbed. On the left, you can see two robotic arms. The ceiling-mounted robotic arm is holding a camera, and the images from this camera are shown on the right. The robotic arm that is mounted to the ground is holding a 3D printed model of the asteroid Eros. High-fidelity dynamics models dictate the motion of the spacecraft camera relative to the asteroid, so that the spacecraft camera can capture images of the asteroid similar to what would actually be encountered in a real mission. So part of my PhD research has also been developing the software for controlling these robotic arms.
I want to end by giving a big thank you to ARCS for funding my research. I plan to follow the mission of ARCS to advance science and technology in the United States by working for NASA Goddard after I graduate.